All right, I'm going to pick up where I left off from the last one. We're looking at a watershed map, America's watersheds. We're looking at watersheds that feed into the Mississippi River. And I want to pay attention to what is taking place here at the Gulf of Mexico here. Right here where we're in New Orleans, in Louisiana. That all of this sediment and debris that's deposited here, right, that builds this delta, the river water from the Mississippi, it's bringing debris, sediment with it. And within that sediment, we're talking about fertilizers. This is all the watersheds that are literally draining or essentially taking with it chemical and physical components of the land itself. And with that, we're bringing nitrate and phosphate. These are fertilizers. These are how we keep the heartland growing. You know, this is where we get our food sources, our corn, our wheat, our soybeans, etc. And all of this travels downstream. It just takes different paths to get there. So you can look at different densities or concentrations of nitrogen, right? Nitrogen yield here, just different topical, let's just say it's the fertilizer that's added to help add nutrient to the soil. That's going to help the plants, our foods grow. And as a result of this, they get transported down here into the Gulf of Mexico. And this leads to something called the dead zone. So the dead zone in the Gulf of Mexico, and this is at the mouth of the Mississippi River, is tremendously large. This is where in this case, the Mississippi River kind of ends up. And if I look here, there's just a high concentration, and this is essentially eutrophication taking place. This is the lack of dissolved oxygen, right, at depth due to unhealthy levels of nitrate and phosphate. You get this very low oxygen level. And organisms don't like to be where they can't breathe. That would be kind of hard for you and me. So here's a different type of picture here. And if I were to show you a picture over time, or images over time, this actually fluctuates. At times it's larger, at times it's actually smaller. But it's no less exists, and this is something that's kind of a current problem, that this is what's called a non-point source pollution, that this is actually doing damage, and it actually comes from the Midwest. So this area is doing damage here, called a non-point source pollution. So here we can relate the concept of deposition. The sediment that's being transported in the river is going to be based on kinetic energy. So if I look at larger sediment called coarse sediment, and I can talk about smaller sediment, fine. Clay and silt-sized particles are very tiny. It doesn't take much energy to transport them, whereas sand grains are often considered medium. And larger sediment are gravel-sized sediments. Gravel is kind of this term of coarse. It's large, right? They're, I would say, larger, your fingernail, roughly. And so the idea here is a relationship of kinetic energy to the size of the particle. The greater the size, it takes faster moving water or greater kinetic energy to move a coarse-sized particle. So to have gravel move along the bed load, it takes water moving relatively quickly. But fine or smaller sized particles, it doesn't take much kinetic energy. Water that's moving relatively slowly can handle it. It just has enough energy to carry tiny particles. So the size of the particle that's transported is directly dependent on the kinetic energy. So I'm going to play this little video animation. And
this animation is going to show how water has kinetic energy. And as the kinetic energy, as it travels from, in the case of the picture at the beginning, as the velocity goes from the channel into a larger area, the velocity decreases, right? The decreasing velocity of streamflow. And as a result of that, the sediment, the gravel-sized sediment, is going to be deposited out. And what we're going to get here is that the kinetic energy is going to be moving these sediments, right? We've determined that streamflow is the volume of flow, the width and the depth and the velocity together are going to coincide, and they're going to drop off the largest, the coarsest particles first, the gravel-sized sediment first, right? Because as your kinetic energy changes, the sediment's going to be deposited. And then next are going to be your sand grains. And then lastly, it doesn't take much kinetic energy or energy to move clay-sized particles, and they'll be deposited last.
So kinetic energy in water is what moves sediment. So dissolved material travels in solution of the moving water. Fine particles, such as silt and clay, are tiny in size. They're what become muds that we talk about. These get transported as suspensions in moving water. This is what we measure when we study and calculate turbidity. Coarser particles, pebbles, cobble, and gravel, are large in size, visible to the naked eye. They are too heavy to be moved as suspension. These move along the stream bed in a series of jumps and rolls. Angular or jagged rocks get smoothed out as they're transported, so they become rounded as they travel. This is a form of physical or mechanical weathering. There is no change in the rock's composition. If it were a change in the composition, that would be considered chemical weathering, but it's not. It's physical. And this process is called abrasion. During chemical weathering, there's a change in the composition of the object. For example, rust. Rust is from the process of oxidation. So here we're going to watch a little bit of this video.
In this animation, we're going to be able to see how moving water, having kinetic energy, is going to be able to transport different types of sediment. We can look at the material that's moving with the kinetics of the water and along the riverbed. And these are larger. These are coarser sized particles. And we would call these pebbles, gravel, and or cobble. Those are just referring to the sizes of the objects themselves. In this case, up above, we see material that is suspended. A suspension is something that is able to be, let's just say, contained and held within the energy, the kinetic energy of the moving water. And then lastly, what we can't quite see would be the extremely fine sediment. Right, this material here would be fine, but some of it gets dissolved into the water itself. And so we can look at these as a couple different ways. We could say that the gravel, rocks, and boulders move downstream by sliding or rolling, and these actually gradually round off over time. Rounding is a normal process of physical or mechanical weathering. It is called abrasion because you go from these angular pieces to becoming rounded. Sand can also be rounded off as well, and then it's the silt and clay that we measure in terms of turbidity, right? They're suspended in the water. And lastly, the finest of material that we test with the Hawk spectrophotometer is the material that is dissolved, and this is considered to be in solution.
So let's put it all together. We start talking stream dynamics. There's a lot going on. It's important that we kind of slow down, and I like the visual aspect, so I'll try to talk you through these pictures. So moving water flowing through a channel has kinetic energy. Kinetic energy mathematically is represented as 1/2 mass times velocity squared. So kinetic energy in water carries sediment with it, and it can erode land, erosion, along a cut bank. As water turns along a bend, it erodes the outer part of that very bend, right? Water moving along here. Erosion taking place on the outside, deposition takes place along the inside. Here's another one. Here's the direction of the arrows, so it's moving this way. You're getting erosion and deposition. You get this sequence: erosion, deposition, erosion on the outside, deposition, erosion, deposition. And so over time, as a river ages, you're actually getting more meander, and this is a term that we refer to as sinuosity. It has a greater sinuosity, where this here would be younger. It just has less sinuosity to it. And this would be a little bit straighter, so this would be even younger yet. So as water flows downstream, the outside of the bend of the river gets eroded, while the inside is a location of deposition, right? Sediment is deposited. It could be muds and sands, etc. But as the velocity changes, it doesn't have the kinetic energy to transport sediment, so it drops it out. So on the right here, riffles and pool systems. These are what we have here in the Middle Fork River. These are located in pairs. We have a riffle pool system. Riffles increase the surface area of the water with atmospheric oxygen, thus creating the dissolved oxygen, or increasing the dissolved oxygen of the water, and thus increasing its overall health. So a riffle system actually can be very, very positive to increase the overall health of the river, just like the river that we look at and we test our samples in. Discharge, or streamflow, volumetric flow. Now, although this topic here has been something we've looked at numerous times, I want to make sure we understand what we're doing when we look at these river channels. So we're talking streamflow, right? Discharge. How much volume of water is flowing? Well, streamflow changes regularly and periodically. Droughts decrease the volume of water moving in a channel as precipitation and flooding increase the amount of water moving in a channel. So if we look at the picture, water is moving at its max velocity at very specific locations in both a symmetrical and an asymmetrical channel. The cross-section profile allows us to view the shape, right, the topography of the river channel. The measurements that we take in class allow us to create and form a graph that illustrates the channel contour. So we're able to do that. But if I look at a symmetrical river channel, you'll see that where the maximum velocity is located is actually located at the deepest part of the water. The reason is because it has it's furthest from the frictional drag with the bottom of the body of water itself, or the surrounding land itself. As water comes across in contact with the riverbed, it's going to slow down, frictional drag. And an asymmetrical channel, you'll notice that it's located over here. It's just the furthest distance from the greatest net frictional drag. So stream flow is average width times average depth times average velocity. So where we find the maximum velocity is where we find the deepest part of the water, or deepest part of the river. Friction between the water and the channel slow or impede the water's velocity. So find the deepest water, you find the greatest rate of flow as that channel, or as that water is flowing downstream. So this picture here, we're looking at different terrain. This is a very steep terrain, and this is a very flat terrain. But we're going to look at gradient. The gradient has tremendous importance here. So here goes. V-shaped valleys. When we look at a mountain stream, often they're found or located in this V-shaped structure, right? A V-shape here. It's because water down cuts through even very resistant rock. The river is literally following a tremendous gradient, right? The slope. And that's actually having the water be somewhat, it's kind of like a knife. It's cutting into the even very resistant rocks, such as like granite. But the Colorado River here, here's a picture I want to pay attention to. This is kind of a unique situation. It down cuts through the resistant rock, not because of the steep gradient, but because the land was uplifted beneath the water itself. So water does the cutting as the land itself was uplifted. Flooding. Satellite views of the confluence of the Missouri River flowing into the Mississippi River here show a very obvious scenario of dramatic flooding. And this here is the picture. So here's a picture of extreme drought. Here's an extreme flood. So St. Louis is just south of the confluence. The left image shows the rivers during a drought in the summer of 1988. Whereas the picture to the right depicts the peak of the record-breaking 1993 flood. Exceptional rains produced the wettest spring and early summer in the 20th century in the upper Mississippi River Valley, or river basin. Nearly 14 million acres were inundated, displacing at least 50,000 people. So flooding is kind of something we hear about. So here we have a levee that actually broke, and it's kind of just like a release valve. Imagine all this tremendous amount of water that's contained in this channel. Imagine there being some kind of berm or hill that breaks, and all this water would just flood in here. Well, what happens is that these levee breaks, the water put so much pressure on them, it couldn't understand the force of the flood water. The levee just broke and just inundated the land here. So let's look at lag time. This is a lag time graph. This is where we find rainfall and flooding here. I want to pay attention to the x-axis of time for a second. So the discharge. So if we have a heavy rainfall at time x here, the flooding doesn't occur instantaneously. It takes a while. It takes a while for water to flow off the land and reach the river channel, right? It has to flow downhill and flood the actual, whatever the body of water is. And this is the difference in time. It's called lag time. So I can look at this a little different. If I get this high rainfall event, an urbanized watershed, right, like a suburbia where there's a ton of pavement and homes, development, that water is going to flow from concrete. It's going to flow faster than an unurbanized or a non-urbanized, like a rural area. Notice the lag times differ. It used to be this before it was developed, but the lag time is much shorter, quicker. Still not instantaneous, but much quicker. And the world's largest rivers. Here you can take a look at the drainage area and the average discharge, and a little something for you to view.